Compass-and-straightedge construction, also known as ruler and compass construction or classical construction, is the construction of lengths, angles, and other geometric figures using only an idealized ruler and compass. The idealized ruler, known as a straightedge, is assumed to be infinite in length, and has no markings on it and only one edge. The compass is assumed to collapse when lifted from the page, so may not be directly used to transfer distances. More formally, the only permissible constructions are those granted by Euclid's first three postulates. Every point constructible using straightedge and compass may be constructed using compass alone. The ancient Greek mathematicians first conceived compass and straightedge constructions, and a number of ancient problems in plane geometry impose this restriction. The ancient Greeks developed many constructions, but in some cases were unable to do so. Gauss showed that some polygons are constructible but that most are not. Some of the most famous straightedge and compass problems were proven impossible by Pierre Wontesil in 1837, using the mathematical theory of fields. In spite of existing proofs of impossibility, some persist in trying to solve these problems. Many of these problems are easily solvable provided that other geometric transformations are allowed. For example, doubling the cube is possible using geometric constructions, but not possible using straightedge and compass alone. In terms of algebra, a length is constructible if and only if it represents a constructible number, and an angle is constructible if and only if its cosine is a constructible number. A number is constructible if and only if it can be written using the four basic arithmetic operations and the extraction of square roots but of no higher order roots. Compass and straightedge tools. The compass and straightedge of compass and straightedge constructions are idealizations of rulers and compasses in the real world. The compass can be opened arbitrarily wide, but it has no markings on it. Circles can only be drawn starting from two given points, the center and a point on the circle. The compass may or may not collapse when it's not drawing a circle. The straightedge is infinitely long, but it has no markings on it and has only one straight edge, unlike ordinary rulers. It can only be used to draw a line segment between 2 points or to extend an existing segment. The modern compass generally does not collapse and several modern constructions use this feature. It would appear that the modern compass is a more powerful instrument than the ancient collapsing compass. However, by Proposition 2 of Book 1 of Euclid's Elements, no power is lost by using a collapsing compass. Although the proposition is correct, its proofs have a long and checkered history. Each construction must be exact. Eyeballing it and getting close does not count as a solution. Each construction must terminate. That is, it must have a finite number of steps, and not be the limit of ever closer approximations. Stated this way, compass and straightedge constructions appear to be a parlor game, rather than a serious practical problem. But the purpose of the restriction is to ensure that constructions can be proven to be exactly correct, and is thus important to both drafting and the science of weights and measures, in which exact synthesis from reference bodies or materials is extremely important. One of the chief purposes of Greek mathematics was to find exact constructions for various lengths. For example, the side of a pentagon inscribed in a given circle. The Greeks could not find constructions for these three problems, among others, squaring the circle, drawing a square the same area as a given circle. Doubling the cube, drawing a cube with twice the volume of a given cube. Trisecting the angle, dividing a given angle into three smaller angles all of the same size. For 2,000 years people tried to find constructions within the limit set above, and failed. All three have now been proven under mathematical rules to be impossible generally. History. The ancient Greek mathematicians first attempted compass and straightedge constructions, and they discovered how to construct sums, differences, products, ratios, and square roots of given lengths. They could also construct half of a given angle, a square whose area is twice that of another square, a square having the same area as a given polygon, and a regular polygon with 3, 4, or 5 sides. But they could not construct 1/3 of a given angle except in particular cases, or a square with the same area as a given circle, or a regular polygon with other numbers of sides. nor could they construct the side of a cube whose volume would be twice the volume of a cube with a given side. Hippocrates and Menelaus showed that the area of the cube could be doubled by finding the intersections of hyperbolas and parabolas, but these cannot be constructed by Compass-and-straightedge. In the 5th century BCE, Hippias used a curve that he called a quadratrix to both trisect the general angle and square the circle, and Nicomedes in the 2nd century BCE showed how to use a conchoid to trisect an arbitrary angle. But these methods also cannot be followed with just Compass-and-straightedge. No progress on the unsolved problems was made for 2 millennia, until in 1796 Gauss showed that a regular polygon with 17 sides could be constructed. 5 years later he showed the sufficient criterion for a regular polygon of n sides to be constructible. In 1837 Pierre Wontezel published a proof of the impossibility of trisecting an arbitrary angle or of doubling the volume of a cube, based on the impossibility of constructing cube roots of lengths. He also showed that Gauss's sufficient constructibility condition for regular polygons is also necessary. Then in 1882 Lindemann showed that is a transcendental number, and thus that it is impossible by straightedge and compass to construct a square with the same area as a given circle. The basic constructions. All compass-and-straightedge constructions consist of repeated application of 5 basic constructions using the points, lines and circles that have already been constructed. These are, creating the line through 2 existing points, creating the circle through one point with center another point, creating the point which is the intersection of 2 existing, non-parallel lines, creating the 1 or 2 points in the intersection of a line and a circle, creating the 1 or 2 points in the intersection of 2 circles. For example, starting with just 2 distinct points, we can create a line or either of 2 circles. If we draw both circles, 2 new points are created at their intersections. Drawing lines between the 2 original points and one of these new points completes the construction of an equilateral triangle. Therefore, in any geometric problem we have an initial set of symbols, an algorithm, and some results. From this perspective, geometry is equivalent to an axiomatic algebra, replacing its elements by symbols. Probably Gauss first realized this, and used it to prove the impossibility of some constructions. Only much later did Hilbert find a complete set of axioms for geometry. Much used compass-and-straightedge constructions. The most used compass-and-straightedge constructions include, constructing the perpendicular bisector from a segment, finding the midpoint of a segment. Drawing a perpendicular line from a point to a line. Bisecting an angle, mirror a point in a line, construct line through a point tangent to a circle. Constructible points and lengths. Formal proof equals, there are many different ways to prove something is impossible. A more rigorous proof would be to demarcate the limit of the possible, and show that to solve these problems one must transgress that limit. Much of what can be constructed is covered in intercept theory. We could associate an algebra to our geometry using a Cartesian coordinate system made of 2 lines, and represent points of our plane by vectors. Finally we can write these vectors as complex numbers. Using the equations for lines and circles, one can show that the points at which they intersect lie in a quadratic extension of the smallest field f containing 2 points on the line, the center of the circle, and the radius of the circle. That is, they are of the form, where x, y, and k are in f. Since the field of constructible points is closed under square roots, it contains all points that can be obtained by a finite sequence of quadratic extensions of the field of complex numbers with rational coefficients. By the above paragraph, one can show that any constructible point can be obtained by such a sequence of extensions. As a corollary of this, one finds that the degree of the minimal polynomial for a constructible point is a power of 2. In particular, any constructible point is an algebraic number, though not every algebraic number is constructible. For example, is algebraic but not constructible. Constructible angles. There is a bijection between the angles that are constructible and the points that are constructible on any constructible circle. The angles that are constructible form an abelian group under addition modulo 2I euro. The angles that are constructible are exactly those whose tangent is constructible as a number. For example, a regular heptadecagon is constructible because, as discovered by Gauss, the group of constructible angles is closed under the operation that halves angles. The only angles of finite order that may be constructed starting with 2 points are those whose order is either a power of 2, or a product of a power of 2 and a set of distinct Fermat primes. In addition, there is a dense set of constructible angles of infinite order. Compass-and-straightedge constructions is complex arithmetic, given a set of points in the Euclidean plane, selecting any one of them to be called 0 and another to be called 1, together with an arbitrary choice of orientation allows us to consider the points as a set of complex numbers. Given any such interpretation of a set of points as complex numbers, the points constructible using valid compass-and-straightedge constructions alone are precisely the elements of the smallest field containing the original set of points and closed under the complex conjugate and square root operations. The elements of this field are precisely those that may be expressed as a formula in the original points using only the operations of addition, subtraction, multiplication, division, complex conjugate, and square root, which is easily seen to be a countable dense subset of the plane. Each of these 6 operations corresponding to a simple compass-and-straightedge construction. From such a formula it is straightforward to produce a construction of the corresponding point by combining the constructions for each of the arithmetic operations. More efficient constructions of a particular set of points correspond to shortcuts in such calculations. Equivalently, we can say that, given an arbitrary choice of orientation, a set of points determines a set of complex ratios given by the ratios of the differences between any 2 pairs of points. The set of ratios constructible using compass-and-straightedge from such a set of ratios is precisely the smallest field containing the original ratios and closed under taking complex conjugates and square roots. For example, a real part, imaginary part and modulus of a point or ratio z are constructible as these may be expressed as doubling the cube and trisection of an angle require ratios which are the solution to cubic equations, while squaring the circle requires a transcendental ratio. None of these are in the fields described, hence no compass-and-straightedge construction for these exists. Impossible constructions. The ancient Greeks thought that the construction problems they could not solve were simply obstinate, not unsolvable. With modern methods, however, these compass-and-straightedge constructions have been shown to be logically impossible to perform. Squaring the circle equals. The most famous of these problems, squaring the circle, otherwise known as the quadrature of the circle, involves constructing a square with the same area as a given circle using only straightedge and compass. Squaring the circle has been proven impossible, as it involves generating a transcendental number, that is, only certain algebraic numbers can be constructed with ruler and compass alone, namely those constructed from the integers with a finite sequence of operations of addition, subtraction, multiplication, division, and taking square roots. The phrase squaring the circle is often used to mean doing the impossible for this reason. Without the constraint of requiring solution by ruler and compass alone, the problem is easily solvable by a wide variety of geometric and algebraic means, and has been solved many times in antiquity. Doubling the cube equals. Doubling the cube, using only a straight edge and compass, construct the edge of a cube that has twice the volume of a cube with a given edge. This is impossible because the cube root of 2, though algebraic, cannot be computed from integers by addition, subtraction, multiplication, division, and taking square roots. This follows because its minimal polynomial over the rationals has degree 3. This construction is possible using a straightedge with 2 marks on it and a compass. Angle trisection equals. Angle trisection, using only a straightedge and a compass, construct an angle that is 1/3 of a given arbitrary angle. This is impossible in the general case. For example, though the angle of I/3 radians cannot be trisected, the angle 2I/5 radians can be trisected. This problem is also easily solved when a straightedge with 2 marks on it is allowed. Constructing regular polygons. Some regular polygons are easy to construct with straightedge and compass. Others are not. This led to the question, Is it possible to construct all regular polygons with straightedge and compass? Carl Friedrich Gauss in 1796 showed that a regular 17-sided polygon can be constructed, and 5 years later showed that a regular n-sided polygon can be constructed with straightedge and compass if the odd prime factors of n are distinct from at primes. Gauss conjectured that this condition was also necessary, but he offered no proof of this fact, which was provided by Pierre Wontezel in 1837. The first few constructible regular polygons are 3, 4, 5, 6, 8, 10, 12, 15, 16, 17, 20, 24, 30, 32, 34, 40, 48, 51, 60, 64, 68, 80, 85, 96, 102, 120, 128, 136, 160, 170, 192, 204, 240, 255, 256, 257, 272. Distance to an ellipse. The line segment from any point in the plane to the nearest point on a circle can be constructed, but the segment from any point in the plane to the nearest point on an ellipse of positive eccentricity cannot in general be constructed. Constructing with only ruler or only compass, it is possible to construct anything with just a compass if it can be constructed with a ruler and compass, provided that the given data and the data to be found consist of discrete points. It is impossible to take a square root with just a ruler, so some things that cannot be constructed with a ruler can be constructed with a compass. But given a single circle and its center, they can be constructed. Extended constructions. Markable rulers equals. Archimedes and Apollonius gave constructions involving the use of a markable ruler. This would permit them, for example, to take a line segment, 2 lines, and a point, and then draw a line which passes through the given point and intersects both lines, and such that the distance between the points of intersection equals the given segment. This the Greeks called neusis, because the new line tends to the point. In this expanded scheme, any distance whose ratio to an existing distance is the solution of a cubic or a quartic equation is constructible. It follows that, if markable rulers and neusis are permitted, the trisection of the angle and the duplication of the cube can be achieved. The quadrature of the circle is still impossible. Some regular polygons, like the heptagon, become constructible. And John H. Conway gives constructions for several of them. But the 11-sided polygon, the hendecagon, is still impossible, and infinitely many others. When only an angle trisector is permitted, there is a complete description of all regular polygons which can be constructed, including above-mentioned regular heptagon, triskaidekagon and enneadecagon. It is open whether there are infinitely many primes p for which a regular p-gon is constructible with ruler, compass and an angle trisector. Allowing the use of neusis or angle trisector makes the following additional regular polygons also constructible: 7, 9, 13, 14, 18, 19, 21, 26, 27, 28, 35, 36, 37, 38, 39, 42, 45, 52, 54, 56, 57, 63, 65, 70, 72, 73, 74, 76, 78, 81, 84, 90, 91, 95, 97. The first few regular polygons not constructible even allowing neusis or angle trisector are 11, 22, 23, 25, 29, 31, 33, 41, 43, 44, 46, 47, 49, 50, 53, 55, 58, 59, 61, 62, 66, 67, 69, 71, 75, 77, 79, 82, 83, 86, 87, 88, 89, 92, 93, 94, 98, 99, 100. Origami equals. the mathematical theory of origami is more powerful than compass-and-straightedge construction. Folds satisfying the Husayer-Hattori axioms can construct exactly the same set of points as the extended constructions using a compass and a marked ruler. Therefore origami can also be used to solve cubic equations, and thus solve two of the classical problems. The extension field equals, in abstract terms, using these more powerful tools of either Newsys using a markable ruler or the constructions of origami extends the field of constructible numbers to a larger subfield of the complex numbers, which contains not only the square root, but also the cube roots, of every element. The arithmetic formulae for constructible points described above have analogies in this larger field, allowing formulae that include cube roots as well. The field extension generated by any additional point constructible in this larger field has degree a multiple of a power of 2 and a power of 3, and may be broken into a tower of extensions of degree 2 and 3. Computation of binary digits. In 1998 Simon Plouffe gave a ruler and compass algorithm that can be used to compute binary digits of certain numbers. The algorithm involves the repeated doubling of an angle and becomes physically impractical after about 20 binary digits. See also, constructible number, constructible polygon, Carlyle circle, geometric cryptography, geometrography. Interactive geometry software may allow the user to create and manipulate ruler and compass constructions. List of interactive geometry software, most of them show compass-and-straightedge constructions. Mora-Mascaroni theorem, Poncelet-Steiner theorem, Underwood-Dudley, a mathematician that has made a sideline of collecting false ruler and compass proofs. References: Underwood-Dudley, What to Do When the Trisector Comes, The Mathematical Intelligence of 5, 20/25, doi, 10.1007/BF03023502, Godfred Toussaint, A New Look at Euclid Unregistered Trademark S. Second Proposition, The Mathematical Intelligencer, Volume 15, Number 3 pages 12 to 24. ABCDEFGHI Bold, Benjamin. Famous Problems of Geometry and How to Solve Them, Dover Publications, 1982. Wansel, PML. Recherches sur les moyens de reconnaître registered trademark de un problème de gare copyright Homer copyright tripute c'est rare copyright Sauder avec la règle et le compass. Journal de Math Copyrightmatics Pures et Applica Copywriters. 1-2, 366 €372. Retrieved March 3, 2014. Weierstein, Eric W., Trigonometry Angles, Pi/17, MathWorld. Stewart, Ian. Galois Theory. Pages 75. Squaring the Circle at Makshata, Kazarinoff, Nicholas D. Ruler and the Round. Mineola, New York. Dover pages 29 €30. ISBN 0-486-42515-0. ABHTTP, www.math-edu-msmeekhoffmsmsso7 PDF, H., and Laraji, A., Some Impossible Constructions in Elementary Geometry, Mathematical Gazette 88, November 2004, 548 €551. Conway, John H. and Richard Guy, The Book of Numbers, Gleason, Andrew, Angle Trisection, The Heptagon, and the Triskaidekagon, Amma. Math. Monthly 95, Number 3, 185-194. Rowe, T. Sundara. Geometric Exercises in Paper Folding. New York, Dover. Simon Plouffe. The Computation of Certain Numbers Using a Ruler and Compass. Journal of Integer Sequences 1. ISSN 1530-7638. External links, Online Ruler and Compass Construction Tool, Regular Polygon Constructions by Dr. Math at the Math Forum at Drexel, Construction with the Compass Only at Cut the Knot, Angle Trisection by Hippocrates at Cut the Knot, Weierstein, Eric W., Angle Trisection, MathWorld. Various constructions using compass-and-straightedge with interactive animated step-by-step instructions. Math tricks help you design shop projects. Master a simple compass and you're a designer. Convert your router into one with a trammel and away you go. Popular Science, May 1971, p. 104106108. Scanned article via Google Books, http://books.google.com/. Books ID == PG = PA104, visual Euclid slideshows of Euclidean constructions.